All right, so we're going to move into rational functions. So rational functions are kind of an extension of your polynomials. So your rational functions are a quotient of polynomial functions. So that means that rational functions can be expressed as fx is equal to px over qx, where p and q are both going to be polynomials. And we just have the one little extra rule here that q cannot be a function that's just equal to 0, because then otherwise fx is just completely undefined everywhere. The domain of a rational function is the set of all real numbers except the x values that make the denominator 0. So we already did look at domains of rational functions. We're just going to do like a quick recap on that, kind of get us where we need to go, and then we're going to move forward. So just as, like I said, a quick reminder, we want to find the domain of this function here. So we have x squared minus 25 over x minus 5. Now, what we'd always said before is we're really only concerned about when the denominator is equal to 0. Because remember, if you have anything divided by 0, this becomes undefined. So that also means 0 divided by 0, to keep this uniform, is also undefined. So it doesn't matter what the number is. If we divide by 0, it suddenly becomes undefined, even if it's 0 divided by 0. Okay, so we just want to find the domain of this function. So the reason I bring up the undefined part is that some of you, because we had practiced this before, doing simplification, remember that we can break it up like this, and this x minus 5 gets eliminated. So remember, before you try to do anything like that, you need to use the original function and find the domain. So the domain is when x minus 5 is simply just not 0. So when is it 0? So x minus 5, we said we've seen this before, is 0 as long as x is equal to 5. So what that means is the domain is when x minus 5 is not equal to 0, or when x itself is not equal to 5, because that is when x minus 5 is equal to 0. So we wrote our domain two different ways. We say x such that x is real, and x is simply not 5. Or we have the other notation, which is we go from negative infinity, we hit every x value up to 5. We don't include 5 because we're skipping over it. And then we go to the other side of 5 and continue on to infinity. Okay. Let's do another example just to remind us. So we want to find the domain of this rational function. So we got x over x squared minus 25. So if we factor the bottom, we get x minus 5, x plus 5. So what we want to see is when is x minus 5, x plus 5 equal to 0, because we can't have 0 in the denominator. So that will either happen when x is equal to 5 or x is equal to negative 5. So our domain, so we're going to say x such that x, I'm going to shorthand this. So this part here just means x is a real number. Because x is a real number, and x cannot be negative or positive 5. Or you'd say, we go from negative infinity and then we hit negative 5. We have to skip over it, start on the other side of negative 5, and then we continue having x values that work up until we hit the positive 5. So we have to stop before we hit it. Then we move to the other side of 5 and we continue for infinity. All right, and then one more example, one we didn't see quite as much. What if we have x plus 5 over x squared plus 25? When is x squared plus 25 equal to 0 in the real numbers? So we're looking for real solutions. So when we deal with rational functions, we are just in the real numbers. You can look in the complex numbers, but we're not going to focus on that part. We're only looking for the real numbers. We're only concerned about the domain of real numbers. So when is x squared plus 25 equal to 0? Well, let's look at that. Well, if I try to get x squared alone, I have to subtract 25. So x squared is equal to negative 25. So if we try to figure out what x is, it's plus or minus the square root of negative 25, which in the real numbers, this is undefined. We cannot do a square root of a negative in the real numbers. So that's undefined, meaning there is no solution to this. Therefore, what we'd see is that x squared plus 25 is never equal to 0 for all x in the real numbers. So what we see here is we don't have anything to remove from the domain. Domain is x such that x is a real number. We have nothing that we remove from the domain. So then we could also say we have everything from negative infinity to infinity. A little bit of notation. This notation is going to help us get into something called limits later on if you progress into calculus. So we use arrows to describe behavior of some functions. So if I have x and this arrow a plus, what that means, so let's say you have something that looks like this. And here's a. Let's say this is b. So this is the point here. So what this first part means is x is getting closer, it's approaching a, but it's approaching it from the positive values, which would be positives over here, negatives over here. So we're approaching from this direction. So we're approaching from the right. Now, let's pick a new color, green. If I have x is equal to a, when it's got that negative on it, that means we're approaching from the negative side now. And that means we're approaching that a from the negative side. So we're getting closer and closer and closer to it from the left. Then the last part, those ones make a little more sense. So what we have here is x is approaching infinity, meaning x is going this way. So x is approaching infinity. And this way means x is approaching negative infinity. So we're trying to figure out what's happening to my x values as I go toward positive infinity. What happens to my x values as I go to negative infinity? So we use this example here. As x approaches a from the right, your y value would be b. As x approaches a from the left, your y value would be b. Sometimes they're going to be different, but right now they're going to be b. As x goes to infinity, we see that my y values also will go to infinity. And on this side, we see that as my x values go to negative infinity, my y values get closer and closer to 0 here. Maybe your y is approaching 0. Okay, so we're going to expand on this just a little bit more because we're going to move into something called asymptotes. The line x plus a is a vertical asymptote of the graph of the function f if fx increases without bound as x approaches a. So here's my a, and what we have is two things going on. So in this case, what we have is x is approaching a from the right, because that's where my asymptote is on this side. So as I approach from the right, let me pick a new color for this. That shows up a little better. As I approach, and my x values keep going, my y values keep on going up and up and up and up and up. So we get fx, this is our y, is approaching infinity. So we will call this line here a vertical asymptote. So don't forget about asymptotes, because you will have asymptotes again in pre-cal. And we would call this line, because this is a vertical line going through x equals a. It's going to be a vertical asymptote, x equals a. Or you just call it x equals a. On this side, we are approaching a. So here's my a, my x value. I'm approaching from the left. So we have x is approaching a, but from the left. And this time what happened, kind of the same thing, because we're going from this direction, is that we see that my y values are also increasing without bound. So they are going to infinity. So as long as you're increasing without bound, so you could also be decreasing as well. So you could have an asymptote go like this as well. So make it red. So I can have a line like this that as I approach, say, x is being approached from the right now, we might see in that case my y values are going down. That'd be negative infinity. That is also an asymptote. So all that happens is that as x approaches this a, you see that your y values are going to go to infinity, or your y values go to negative infinity. So vertical asymptote. Going to be the line x equals a, where if x approaches a, the right or the left, f of x is going to either go to positive or negative infinity. Okay, so this is just showing you from the other side. So here, we're coming at a from the right, and then we see the y values are going down and down, 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 without bound, going towards negative infinity. And then here we're approaching a from the left, and our y values are going to negative infinity. So how do we locate a vertical asymptote? Well, let's go back and look at decimals for a bit. So we see here I got y equals 1 over x minus 1. So we know that this is undefined when x is equal to 1. So what that means is where that spot's undefined, if you notice in the graph, well, this is where 1 is, we get a vertical asymptote. So we get a vertical asymptote here at x equals 1. So various things will happen here, but what we're seeing here is that every place that I'm undefined, that's where I should end up with an asymptote. So let's add to this just a little bit. Let's say now we have, let's do that now. So this is undefined. At x is equal to negative 2 and 1. So we see the line here. And we see that we'd have a line here as well. We're going to go through this just a little bit more because there's a little more to this. So I can keep changing what's going on at the top here. I can have a x minus 2, and we still have those same asymptotes, right? I could have x squared minus 1. And all of a sudden, you see something weird happens when those asymptotes disappears. And it has nothing to do with the square, because if I had 4, oops, sorry, not 4, that was a bad one to pick. If I had 6, those asymptotes are still there. So the problem here is that we're getting asymptotes in a very particular situation. So it's not just where we're undefined, because we're still undefined at these 2 points, because if I click right here, there we go. I had it a second ago. I keep losing it right there. We see at that one where we said the undefined, the graph is still undefined. Technically, there is a hole here in the graph. So let me erase this a second. This goes back to one of the things we were talking about, is that parts of our domain get hidden when we simplify. So if we broke this down, like this, what we see is we get this x minus 1 on the top and the bottom. So that's a place where you'd have 0 over 0, so it's still undefined. But if we look at the simplified form, we just have x plus 1 over x plus 2. So we still have this asymptote at minus 2. The one at negative 1 disappears. That becomes a hole. So the x minus 1 over the x minus 1 gives us a hole. And the x plus 1 that's remaining and the x plus 2 is going to give us the asymptote. So if f is going to be p over q is a rational function which p and q have no common factors. So that last case we saw, we had an x minus 1 on the top and x minus 1 on the bottom. That was a common factor. If we have no common factors and a is a 0 of your bottom polynomial, the denominator, which is the denominator, then x equals a is going to be a vertical asymptote of the graph. So that means if we have x minus 1 and x plus 2, no common factor. So we would see that the vertical asymptote, I'm going to say it's VA, would happen at x is equal to negative 2, because that's where I'm undefined on the bottom. If I had fx is equal to x plus 2 over x plus 2, which you could see this, we can't just say this is 1, because still it's undefined at x equals negative 2. So here we have a common factor, which is x plus 2. So we'd have no vertical asymptote at x equals negative 2. Second, is my way on the screen? What we have is we have a hole at x equals negative 2. Like we see here, we have that vertical asymptote because they're not common factors. However, if I make the top now x plus 2, we get a straight line, but it's still going to be undefined at negative 2. We want to find the vertical asymptotes, if any, of the graph of the rational function. So we have x on top, and I have x squared minus 1 on the bottom. So first thing we want to do is factor everything and see if we got common factors. So x squared plus minus 1 is just going to be x plus 1 times x minus 1. So we are going to see we have no common factors among the top and bottom. So we have no common factors. We are undefined. Fx is undefined. So we see here, we don't want this to be 0, so that would be x minus 1. And we would be here at x plus 1. So we would definitely see we would have a asymptote here and an asymptote here. And if you want to get an idea what the graph is going to look like, just plug in a few points just to get a general idea what it's going to look like. So we have 0 here. So if I plug in 0, I'm going to end up with 0 over negative 1. So this is just going to be 0. If I put in 1, I'm going to have 1 over 1 minus 1. Oh, that's right. Can't use that because we're undefined. Let's say I use like 1/2. Then we're going to have 1/2 divided by 1/2 squared minus 1. That is going to be 1/2 times 4/3. So you should be at 2/3. Okay. Let me get a few more points here. Let me just put this in my calculator and just do it quickly for us. If I can negative backwards a second. My lines are not lining up very well. Let me do that one more time so we can see that a little clearer. X, fx. So once again, if I put in 0, I should end up with f of 0 if we put that in our calculator. We got 0. If we have 1/2, f of 1/2 actually should have been negative 3/2. Oh, sorry, 2/3, not 3/2. If I put in negative 1/2, f of negative 1/2 will end up being a positive 2/3. So we get a point roughly here and roughly here. And we know that these are asymptotes. So we know that the general behavior in the center is I go up here and then I run along my asymptote. And then I go down here and run along my asymptote. So I'm just using some points to get a general idea of like where is it going up and where is it going down. We got 1 here, so let's put in 2. So if I put in 2, I'm going to end up with 2/3. And if I put in negative 2, I'm going to end up with negative 2/3. So I'm not quite sure about the shape quite yet. So let's pick another point. And once we know more about what the graph should look like, it'll be a little less work for us. So let's say we'll put in negative 3 and 3. So 3 is going to give me 3/8. So 3/8 is going to be a little smaller than this point. So it's going to be a little bit down here. And then if I put in positive 3, I end up with negative 3/8. So that point's a little closer up here. So if we kept on going and more points, what you're going to see here, let's just do one more for an example. If I do 4, let me see, that will be 4, 7, So we'll do this roughly 2.7, and then negative is going to be negative roughly 2.27. So if you kept doing this, you're going to get points that are closer and closer and closer to zero. So right now, if we want to get a good idea what these graphs look like, that's what we're going to have to do is we're just going to have to pick a few points. The asymptotes give me an idea of the behavior. So I can see here as I'm going along, the points are going this way. They're getting closer and closer to negative infinity. So I just continue that progress. Here, as I get closer and closer to the asymptote, we see that my y values are getting greater, so they're going towards positive infinity. All right, so now if we have x minus 1 over x squared plus 1, and once again, we want to find the vertical asymptotes. We can't factor the top or bottom. So this is the final form. So I cannot factor further. So I can't factor this any further. So what you're going to see is I have no common factor. So I don't have to worry about holes. I just have to look for asymptote. So I just need to look at when is x squared plus 1 equal to 0. Well, we saw this before. This is a sum of squares. If I try to solve this for x, I'm just going to be looking for x is equal to plus or minus the square root of negative 1, which is undefined. So in that case, we have no vertical asymptotes. We're pretty good. What we see here is that x squared plus 1 cannot possibly be 0, which means we're defined everywhere, which then means we have no vertical asymptote. So we don't always have vertical asymptote. Sometimes we don't. So let me give you a quick graph of this. So I have x minus 1. Oops, sorry, user error here. So what this looks like is you have a point here, and you have a point about here, and I think here's my intercept. So what happens is it comes along here, goes down, over, and then runs along this way. Let me fix that just a little bit. It goes, goes down, over, it kind of goes up a little bit and then runs down like this. But as you see, I have no vertical asymptote. All right, so I'm not going to ask you the graph here because graphing is a little time consuming. Just look to see if we have vertical asymptotes. So these are cases that we can't quite look at, but just remember, you're just focusing on the bottom for the most, well, the top and the bottom. So you're looking for where it's undefined. And if it's not a factor of the top, then it's a vertical asymptote. So take a moment and work on that. Okay, so I already factored these for us. So what we have here is that we are undefined at x equals 2 and 1. The problem that we have here is we have a common factor. Both the top and the bottom share that x minus 2. What that means is that when x is equal to 2, we have a hole. And when x is equal to 1, because that's not a common factor, that is my vertical asymptote. right, and then for g, if I factor that, I get x minus 3 over, and the only thing I can factor at the bottom is x, so x times x squared plus 9. So this is never equal to 0. This, however, can be 0, right? So we have only one place for undefined. We're only undefined at x equals 0. So if we look, we have no common factors. So that one place that I'm undefined is in my vertical asymptote. So we have that x equals 0 is a vertical asymptote. So once again, if we had fx minus 2 over x squared minus 3x plus 2, we see that we have a vertical asymptote at that 1, but the 2, like we said, it's a hole, it's undefined there. So you notice it leaves a little hole in the graph when I get over that spot. Another thing, notice that, oh, not that one. Sorry, next one. So here, this is the x minus 3 over x cubed plus 9x. And we see, once again, it's got an asymptotic behavior at x equals 0. So one of the things to notice here is that x minus 3, that means that the top equals 0 and x is 3. So that is actually going to be a x-intercept. So just bear that in mind for later. Next, we're going to have our horizontal asymptotes. So horizontal asymptotes are going to be a little different. So when you have vertical asymptotes, we never cross a vertical asymptote. As part of their structures is a point that we can't get to because we're undefined at a vertical asymptote. Horizontal asymptotes are not the same. So we never cross a vertical asymptote. It is a place where the function is undefined. So I can never have a x value there. It's not the same for your horizontal asymptotes. So we have the line y equals b is a horizontal asymptote of the graph of fx if fx approaches, if yeah, fx, so that's your y. So y approaches b. So if y approaches b as x goes towards infinity, like we have in this case, x values are going towards infinity, we see that my y values are getting closer and closer to b. Or your y values approach b as your x values get closer and closer to infinity again this way. So we're coming at b, but we're coming at it from underneath. And the same thing here. So notice that this one, we don't cross, this one, we don't cross, this one, we go down, we cross. But what's happening in the long run is that my y values start approaching that b, y gets closer and closer to that b as x goes towards infinity. So we see that just as the definition here is simply that we're looking very, very long run here. So we can cross a horizontal asymptote. So we can cross a horizontal asymptote in the short run. Meaning there's a little place here where that's going to happen, but as your x values go off to plus or minus infinity, so long run is what we're talking about, we do not cross it again. That's one of the big difference here, because everybody usually hears that an asymptote is a place that you can never cross. That's true for vertical asymptote Horizontal asymptotes are a little different because they're not places where you're undefined. You're looking at long run behavior like we did with our polynomials to sort of decide, in the long run how they behaved. It's the same idea here. In the long run, how is this behaving? Well, in the long run, it stops crossing it and just keeps going closer and closer and closer to y equals b. So locating horizontal asymptote. Let me go in back to Desmos here quickly, kind of show you what this is going to mean in a second. So here we have, in the green, we have x over x squared. So what we see here is that as my x values are heading out towards infinity, we see that my y values are getting closer and closer to 0, that x-intercept, or x-axis. We also see on this side, as x gets closer and closer to negative infinity, so it's going out to negative infinity, that my y values get closer and closer to the x-axis again, so my y values are also approaching 0. So, like I said, as long as x goes to negative infinity or infinity, if my y values start approaching a finite value, then we have a horizontal asymptote. We also have a vertical asymptote, but we're not concerned with that yet. Okay, so let me just turn this off and turn on the next function. So if I turn this one on, this is x plus 3 over x squared minus 7. So what we see here again, we get that same behavior, essentially. So in the middle, it does whatever it's going to do, but when we look long run, what we see is that as my x values go to infinity, my y values go to 0. As my x values go to negative infinity, my y values approach 0. And actually, in this case, as you see, it goes down and under, but it comes up and starts approaching that 0. So long as the degree on top is less than the degree on the bottom, this will always happen. And what it is it's this long-term behavior thing that we have going on. As x values start going towards infinity, we start acting like our leading term. So it's like we saw with long-term behavior. So that means this starts acting like the leading terms, and this really starts to act like x over x squared. So if you look at x over x squared, well, that's just 1 over x. As x gets infinitely bigger, this whole thing gets infinitely smaller. So that's what you're thinking about here. Let me change this a little bit. Now we're going to make the degree on top bigger. So we see here, as x goes towards infinity, so this is x cubed over x, as my x values go towards infinity, my y values are also going towards infinity. They're not approaching anything, they just keep growing. Here, as my x values go to negative infinity, my y values also go towards negative infinity. So what we see here is that we have no horizontal asymptote because my y values don't approach anything, they just grow without bound. So if I have, like that cubed 2, something like this, I have x cubed plus 3 over x squared minus 7. We're going to see something very similar. So we see the same thing here. There's a little bit of this little wiggle here, but in the long run, as my x values, sorry, as my x values start growing, you see y values are growing as well. So as x goes to infinity, y goes to negative infinity. As my x values go to negative infinity, we see my y values are also heading towards negative infinity. So once again, as x heads out to infinity and you're thinking about long-term behavior, we start acting like these leading terms like we saw with polynomials again. So this is really just acting like x cubed over x squared eventually, like I said. I turn the other one back on, even though there was that little jump there, what we see is that the behavior is pretty much the same when you look way, way out. The lines start overlapping. You can't even see the green line anymore. So as that happens, you basically end up with your x cubed over your x, which is just x. So if x is going towards infinity, then your whole function is also going towards infinity. So our very last case, turn off the purple. We'll make this a little more fun. Let me put them out front here. So we're going to put a 3 and a 7. Actually, let's make that an 8 because that'll be easier to see on here in a second. So if I do that, what we see here is that I had 3x squared over 8x squared. And as my x values are going toward infinity, my y values are pretty much staying level here at, let me click on that again, at 0.375 or 3/8. Same thing this way, as x is negative infinity, y is staying level at 3/8. So we have a horizontal asymptote at, and we're going to say it's going to be a y value now. I think I said x earlier on one of them. It should always be y with horizontal asymptotes. It's going to be y is equal to 3/8. If we look at the other version over here, we see the same behavior again. So the short term, it does whatever it's going to do, all kinds of fun stuff, like we saw polynomials. But in the long run, it starts getting closer and closer and closer and closer to, and let me put that in here, y equals 3/8. So it gets closer and closer to that asymptote. And we see that when it goes either to infinity or negative infinity. So same kind of idea here is that as my x values go towards infinity, we start acting like the leading terms. We end up acting like 3x squared over 8x squared, which if you simplify that, it just turns into 3/8. So another way to go about this is just as like this. So we have fx, we got a polynomial on top and a polynomial on bottom. So the degree of the numerator is n and the degree of the denominator is m. So if n is greater than m, or sorry, if n is less than m, so degree on top less than degree on bottom, that's what we're seeing here. Then we have a horizontal asymptote at y equals 0. This case, if n and m are equal, so degree on top equals degree on bottom, then what we're going to see is that we are going to have a horizontal asymptote at y equals the leading terms. So it's going to be, or leading coefficient, is going to be the an over the bm. Or last time we saw that, it's the 3/8. If n is greater than m, so that means the degree of the numerator is greater than the denominator. Degree on top is larger than degree on bottom. Then we have no horizontal asymptote. So we want to find the horizontal asymptote of any of this function here. So what we see is we got the degree of 2 and a degree of 2. So the degree on the top is the same as the degree on the bottom, which means the only thing we look at is basically the 9x squared over the 3x, which is just going to be 9 over 3, which is just going to be 3. So we expect a horizontal asymptote at y equals 3. This one does not have a vertical asymptote, so we don't have to worry about that. So if we looked at this, we have 9x squared over 3x squared plus 1. It's going to have a shape like this. So it comes down and it goes up like this and approaches. And then on this side, pretty much the same shape. So this one's symmetric. But as we see, as x approaches positive or negative infinity, our y values, our fx values, are going to approach 3. So we have a horizontal asymptote is y equals 3. Now we had 9x over 3x squared plus 1. So we got a degree 1 on top and a degree 2 on bottom. Degree on top smaller than bottom, or less than degree on bottom. In that case, we just know that we have a horizontal asymptote. It's going to be y equals 0. Make that in red so we can see that line there. Oops, second, I have a problem with my calculator here. So what we see here is, trying to get the spot in the right place. If you were to graph this, what we do is there's this like little wiggle here. So we go up and then we come down and then we approach 0. And then we go down and then we come back up from underneath and we approach 0. We see here as x head to positive or negative infinity, my y values are approaching that point at 0. So we have a horizontal asymptote of y equals 0. So this is the last case to look at, and then we'll let you guys try this on your own. So we got degree is 3 here. Here our degree is 2. Degree on top is greater than degree on bottom. So in this case, what we have is no horizontal asymptote. Degree 3. So what this does, I make a little graph of it, is it comes up almost like a straight line, does a little squiggle here, and it just keeps on going. So we see that as goes toward positive infinity, y goes toward infinity. As goes towards negative infinity, y values are heading toward negative infinity. So we have no horizontal asymptote. So next question is just find the horizontal asymptotes of the following rational functions. So you have 5x squared minus 2x over x squared minus 3x plus 2. And then you have x minus 3 over x cubed plus x minus 1. So for the top, hopefully a chance to do this, but we see that we've both got a degree 2 polynomial on top and bottom. So in this case, we're just using those leading terms. So we know that y, our horizontal asymptote, is going to be y is equal to 5 over 1, or for us, just y is equal to 5. So here we have this x has got a power of 1, so a degree of 1, and then a degree of 3 on bottom. So the degree on top is less than the degree on bottom. If that happens, then we just know that we're going to have a horizontal asymptote at y equals 0. In the other cases, if the degree is greater on top, then we'd have no horizontal asymptote. And then for your last problem, you have h is equal to x squared minus 5x plus 6 over x cubed minus 9x. And we just want to find both vertical and horizontal asymptotes. Take a moment and work on that. All right, so if we're trying to find these asymptotes, so we have here our horizontal asymptote would be found by looking at the degree. So the degree on top is 2, degree on bottom is 3, degree on top is less than the bottom. So we would have y equals 0 is my horizontal asymptote. Vertical asymptote, if we factor this turns into x minus 3 times x minus 2 over x times x minus 3 times x plus 3. So what we see here is that, pick a different color. This is a common factor. So we know that here, this is where x would be equal to 3. This is going to be a whole. So the other two, we don't have any other common factors in that. We just have this here and this here. They're going to be my other places where I'm undefined. So we see that we're going to have a vertical asymptote at x equals 0 and a vertical asymptote at x equals negative 3. So here's the graph. We can see those asymptotes here. So we jump over, but we approach slowly y equals 0. And we approach from this side as well. We see here, this is where x is equal to 0. We have an asymptote. And where x is equal to negative 3, that's an asymptote. And then so that should be a hole. I'm not sure why it's not giving me a hole there. So sometimes you got to be careful. This gets a little confused. Yeah, that should have been a hole. So right here, we should have a hole in the graph. Like I said, sometimes just be careful with Desmos. It gets itself a little confused. I'm just double checking. Yeah, that should be a hole. Like I said, I don't know why it's not showing up on there, but that should be a hole, not where it's equal to 0. Desmos is nice to show you a lot of things, but it gets a little confused about the way it calculates things. Sometimes it throws off your calculations. That's why we need to know how to do this by hand because of problems like that. We know it's supposed to be a hole most of them.